I'm Bruce Fouke from the University of Illinois in the departments of geology, microbiology, and the Institute for Genomic Biology. The search for life on other planets, the understanding of how life emerged on our own planet, it's a complicated and integrated endeavor to understand what's been happening and what's going to happen in the future. So the scientific field that's been developed for this is called astrobiology. And astrobiology has been defined as the study of the origin, the evolution, the distribution, and the future of life as we know it on Earth, but also life elsewhere within the universe. Now, the field of astrobiology basically has three fundamental questions that it wants to go after. The first one is, how did life itself begin and how did it evolve? It's been on the tips of our tongues as human beings since the dawn of time. Where are we from and what's the meaning of our life? And that's a core piece of the astrobiology initiative. Another really important part of astrobiology is, does life exist elsewhere in the universe? And if so, what is the composition of that life? And then the kind of unifying theme of that is that the history of life on our planet, and then highly probable, potentially, life on other planets. What does the future hold for that? What type of life changes will there be as life in planets and the whole solar system itself evolves through time? So let's look at the idea of astrobiology and the science of it. There's a fundamentally important and inspiring government organization called NASA, the National Aeronautic and Space Administration. And NASA was founded in 1958 in the United States, primarily as a response to the Sputnik 1 launch by the Soviets, and that began the space race. And so NASA has been really the crucible and the melting pot of the idea of astrobiology since that time period. And it's unique because some of these questions in astrobiology are not considered to be core to other primary fields within science. So the NASA mission itself is to be able to answer these questions about the origin of evolution of life, the distribution of life throughout the universe, and then what can we be expecting at some time in the future. Now, NASA has gone about this in a very systematic scientific way, and over the last couple of decades, NASA has brought together hundreds of scientists for large meetings at different locations throughout the U.S. And really the goal of these meetings was to put together what has been now formally coined the NASA Astrobiology Roadmap. And the idea of a roadmap, of course, is that it allows you to predict and plan your journey so that you can actually get to where you want to be. So the roadmap for astrobiology really lays out a perspective of how to go about answering these very important yet extremely challenging and complicated questions that astrobiology is dedicated to. So we're really on the dawn of a new age with the astrobiology roadmap. The fields of physics and chemistry and biology and even social sciences have now merged to be able to answer these questions within astrobiology. And an important caveat of this is that the types of questions that are being approached with astrobiology analyses, they span multiple scales of both space and time. So let's just look quickly at the astrobiology roadmap, and it's composed of 7 fundamental pillars or goals as to what NASA wants to accomplish. The first one is that the goal 1 is to understand the nature and distribution of habitable environments within the universe. Now, this means to use all kinds of technology to have space missions as well as remote sensing, which means that we put up instruments and robots and satellites to be able to take pictures or do analyses in places that we can't go within the universe. But the idea there is to use an integrated approach to determine where else within the universe can life possibly have originated or actually gotten a foothold and evolved from there. And this characterization has been dramatically improved with things like the Hubble telescope, where just within the last year, the number of potentially large enough bodies called planets that are around different stars throughout the universe, the number of those potentially habitable environments has dramatically increased. The second goal is to explore for past and present habitable environments and understand the chemistry of the ancient environments in which this life was either seeded into, in other words, transported from one place to another, or actually originated therein in that place, and therefore have a toolkit to look for signs of life throughout the solar system. So this is heavily weighted upon our knowledge of the chemical composition of life, and then how the chemistry of life comes together to drive the biological composition of life. The third goal or pillar of the roadmap is to understand how life emerged from cosmic and planetary precursors, or pre-existing components of the solar system, fragments of planets, different distributions of gases that have been coming together to cool and congeal to create an environment, a natural laboratory, if you will, in which life might have gotten a foothold. And again, this requires a very integrated toolkit of observation, experimentation, but also theoretical analyses. The theoretical part of this is to take our understandings of how basic physical and chemical processes occur, and then use computer-generated models to make predictions of where we might find this or what the end product of this might have been. Goal 4 is to understand how past life on Earth interacted with an ongoing changing Earth. The Earth itself, as one of the places where life is and potentially is distributed elsewhere, has gone through dramatic changes through its 4.6 billion year history, going from an Earth that had no oxygen to an Earth that was very well oxygenated. And the template, the screenplay, if you will, of astrobiology and the history of our solar system and the search for life is to understand how life itself was interacting with these ongoing changing planetary environments. And we have a back and forth nature where the planet controls what the life can do, but then life emerges to control what the planet can do. And in our own case of planet Earth, the evolution of photosynthesis by bacteria is what actually provided the oxygen that we take for granted on modern day planet Earth. Astrobiology goal number 5 is to understand the evolutionary mechanisms and the environmental limits and constraints on life. So in other words, to take the fundamental concepts of how the mechanisms and processes of evolution work, combine things like the Carl Woese understanding of an RNA world, a progenote, an environment in which we had 3 different branches of life form, and then merging that with the Darwinian understandings of how multicellular life interacts with the environment, bringing together the cutting edge ideas within evolutionary biology and putting them in the context of an evolving planetary system, which planet Earth is the great place to start that process. We still know little, but we've been doing a lot of work as a collective community and understanding how that has taken place on Earth, and that will give us a much better window of what to search for on other planets. Goal number 6 is to understand the principles that will shape the future of life both on Earth and beyond. So we want to understand what are, again, some of these drivers and effects of ecosystem change, because the hallmark here is to have life and environment constantly struggling with each other, one controlling the other, and then having that wrestling match change its emphasis through geological time. So these all are connected together, but these are some of the fundamental stepping stones in terms of the scientific process to understand that. And the final goal 7 is to determine how to recognize signatures of life on other worlds and our early planet Earth. Now, a signature of life, if you go to ancient Rome, you see a signature of life there called the ruins of the Colosseum, the Forum, the Baths of Caracalla. Human signatures of life, one of the nice easy ones is either fossilized bones or ancient structures that still remain. Well, those signatures of life, we also call them biomarkers. And with the humans, it's a little more straightforward. With microorganisms, which is really the life form that we want to track throughout the universe, it's a little more tricky. Because of the size of the organisms, they're very small, and there are non-biological processes that can actually create biosignatures that are similar, either the shape of a crystal, the way a rock is composed in terms of its chemistry and its density, the distribution of different types of chemistries and elements within the rock. These can all be biosignatures, but again, the tricky part is that some non-biological environmental conditions can actually create some of these as well. So understanding the signatures of life on the early Earth, as well as throughout the solar system, is a fundamental part of this. And that's where some of the modern day work that we have on the deep sea vents, Yellowstone National Park and other environments allows us to have a snapshot into what these early Earth environments might have been. So in summary, what astrobiology wants to do is to answer these fundamental questions, the origin and evolution of life, where did we come from, where are we going, and what does the future hold in terms of that distribution of life throughout the universe. And the astrobiology implementation, if you will, the scientific approaches that will yield some of these answers to us, they're really based in three components within the NASA system: space science, earth science, and then human exploration. And so these are tied into both theoretical and practical experimental approaches that range from laboratory analyses to computer analyses to actually putting spacecraft on other planets. And the astrobiology roadmap, one of the things it yields is really it tells us where to put these spacecraft and in what environments to land them on different planets. And it's allowed us to identify things like Mars and Titan and Europa as really key targets within our own solar system that need to be explored first to then extend our understanding of astrobiology from planet Earth to other nearby habitable environments.